which one they're playing, you'll be able to follow our speakers. We'll take questions from reporters online. If you have a question, please dial *1 and you'll be Navy Pacific Missile Range on Kauai, Hawaii. Our Steve Jerzik, Associate Administrator for the Space Technology Mission Directorate at NASA headquarters in Washington. We also have here at PMRF Dr. Mark Adler, the Low Density Supersonic Decelerator Project Manager at NASA's Jet Propulsion Laboratory in Pasadena, California. Also, Dr. Ian Clark, from the Low Density Supersonic Decelerator Principal Investigator, also from JPL. We'll now hear from our speakers today about yesterday's test, and I'll start with Steve.
The team will have met our success criteria for this flight. This is in great measure due to the leadership that both Mark Adler and Ian Clark have provided to an outstanding team that consists of folks from multiple NASA centers, the Navy, and our industry partners. Before I turn things over to Ian and Mark to give you the details of the second supersonic flight dynamics test, I'd like to take a moment to explain why it is so important and imperative that our organization, the Space Technology Mission Directorate, invest in new space technologies. Technology drives exploration and our journey to Mars, and that's why tests such as these are so important in creating new knowledge and keep science and cargo payloads on the surface of Mars. We are also developing other technologies to actually land people, vehicles, and people themselves on Mars, which will require even heavier masses. As I mentioned at our press conference a week ago, we are hoping our supersonic decelerator and parachute performed as planned in this test. It appears everything worked, but while the parachute may have fully inflated, and we need to confirm that with the high-resolution video, it appeared to rupture after deployment. And Ian and Mark will discuss this in more detail in a moment. This is not the first time that physics has pushed back on us on a flight system and tested the limits of our knowledge flight test to expand our knowledge and enable engineering of systems to inform future NASA missions. I'm also confident we will again learn a great deal from this flight and work to develop an effective plan to continue to advance supersonic decelerator technology. I look forward to seeing the high-resolution video and other data, and more importantly, the team's analysis of the data and resulting knowledge we gain as we move forward. And at this point, I'll turn it over to Dr. Adler.
Thank you, Steve. So as Steve said yesterday, we conducted a difficult and complex supersonic experiment in Earth's stratosphere, and it was a successful conduct of that experiment. But the most obvious result of that experiment was a parachute here out of the Pacific Missile Range facility in Kauai. It is a 34 million cubic foot helium balloon that can loft 8,000 pounds to an altitude of 120,000 feet. On that balloon is a 7,000-pound test vehicle that in which we have a Star 48 rocket motor that is used to accelerate the vehicle. Once we drop it at 120,000 feet, that motor accelerates it up to more than Mach 4, and yesterday accelerated it up to 180,000 feet, going at a Mach 4 approximately in a horizontal direction. And then we conduct a test where we deploy our 20-foot diameter supersonic inflatable aerodynamic decelerator at about Mach 3. We then deployed a balloon, which is used to pull out the parachute all the operation. So let me go to roll-in number 1, balloon launch. So I'm going to hit play now. I'll hit play now. There it goes. And so this shows the balloon being released from the spool. The balloon then rises up over the launch tower, which you see in the background there, and now on the right with the test vehicle hanging from it. The balloon goes up. That whole balloon train is about 800 feet long. It rises up into the air. Then the vehicle is released from the tower. That yellow jib swings back to avoid the vehicle hitting it. The vehicle then ascended directly up at about 1,000 feet per minute. It then ascended to our test altitude. We did that launch at about 7:45 a.m. Hawaii time. Yes, we had to wait to be in a good position. So at 11:35 a.m., we then dropped and fired the vehicle. So I'm now running roll-in number 2, drop rocket burn. We see it spin up, and then the large Star 48 rocket motor fire. It fired for 70 seconds and accelerated the vehicle, as I said, up to more than Mach 4 and up a little bit above 180,000 feet. The vehicle was then despun, which we'll see in a second here. You see the balloon in the background. The balloon was ruptured and then fell into the ocean as planned. The rocket motor stopped. The vehicle then shows a little bit of an angle of attack excursion here. We're still looking into that. That's one of the things that didn't happen last year, so it didn't seem to affect the test. We'll here swinging a little bit, and we're going to see the camera lid open and the SIA deploy. The SIAD deployed very nicely, very symmetrically, and maintained rigidity and actually stabilized the vehicle somewhat in flight, so the SIAD was fully successful. Again, this year, as it was last year, we now have a lot of good data on the SIAD. We then deployed this BALU, which is a little yellow object there that's come out. That deployed at about Mach 3, and it worked very well again. It's another one of our bonus technologies that we have on this project that we can use in future flight missions. Then the parachute is deployed, and we see the parachute come out. It appeared to reach full inflation, but then destroyed itself after that. There was a rip in the parachute, and Ian will talk a little bit more about that. Would expect with the parachute in that state. We were able to get the vehicle back, all of the cameras, all of the flight image recorder data. We were able to get back the vehicle itself. We were able to get back the parachute. We also recovered the balloon from the water. All of those things are actually on their way to the port as I speak, and after this press conference, we're going to go over to Port Allen, where the vehicle will be coming into port. We'll be getting the equipment off of it. We have yet to see the actual data on these cards, so once we get it onto port, we're going to be extracting the data off of the memory cards that were stored on the vehicle, and that will tell us whether, in fact, we got a full success on this experiment by getting all of the video data. We're also still in the process of recovering the balloon. So given that those operations complete and that we get the data on the cards, which I fully expect is there, we will have a fully successful experiment. We're then continuing with our work. We have some rocket sled runs of the SIAD coming up in a couple of months. We'll be doing some more testing of the parachute. We need to do an investigation of what happened on this parachute, what our next steps are. We have planned another supersonic flight for next summer, so if we're ready in time for that and we get an understanding of what happened with the parachute, we'll be able to do another test with another iteration of the parachute design. So I'll turn it over to Ian to discuss in more detail the results of the supersonic experiment we conducted yesterday.
And with our vendors and subcontractors as well, and all that they've managed to accomplish. In a few short years, we've developed a number of new aerodynamic decelerators. We've conducted many significant ground-based tests. We've developed new test architectures that, as one commenter put it, make Rube Goldberg look like an amateur. We've successfully conducted numerous rocket sled tests of both our SIADs and our parachutes and out in the desert, and we've twice flown our supersonic test vehicle to the right conditions necessary to test our technologies. The preliminary indications are that the test vehicle once again delivered us to the conditions necessary to test our technologies. The SIAD deployment and inflation, but the SIAD, to its credit, actually served to significantly dampen those and largely recovered the state of the vehicle going into the next phase of the test. The balloon deployed and inflated wonderfully and once again provided incredible drag for us, and it served to help the deployment of the parachute. The deployment of the parachute from the test vehicle appeared to go quite well, and the parachute began inflating uniformly up to the point of full inflation. At some point at or near full inflation, the parachute was damaged, and the damage propagated further until the parachute could no longer survive the harsh supersonic environment. Preliminary look at our load data indicates that the parachute developed full or nearly full drag. Neither of those devices existed previously, and we've now matured them both to the point where they can be used by future planetary missions. As I drove in this morning, I saw sitting off the coast, anchored one of our recovery vessels that had our test vehicle and all of the technologies on board and all of the critical data that we captured during this test. As I speak, it's steaming into port, and in the coming days, we will begin safing and analyzing all of the data that's on board that vehicle. Last year, we rewrote the book on our understanding of supersonic parachutes, and this year, we've got another great set of data to add many more chapters to that tome. In the coming year, we will be a large inflatable drag device, SIAD, that we're continuing to develop and that we have some upcoming tests, rocket sled tests for. We have another supersonic flight test over the skies of Kauai in about a year's time. And so we'll be looking forward to the technologies and the data that will come from that test. Sort of in closing, on this project, we are pushing the limits of our technologies, our engineering, and our understanding of aerodynamic decelerators. This year, the physics of supersonic parachutes pushed back on us. I think as an engineer, this can be a very humbling experience, but as a curious human, this can be extremely exciting with the results that we're seeing this year. And with that, I think we'll take any questions.
Yeah. Please remember to hit *1 to be added to the queue, and I'll let the operator open up the questions.
Thank you. Once again, if you'd like to ask a question, *1. On your touch-tone phone, you'll be asked to state your name prior to joining the queue. Please make sure your mute feature is off and you state your name clearly. Our first question will come from Peter King. Your line is open.
Thanks very much, and good afternoon or good morning to you gentlemen from Peter King, CBS News. I have one question and I have a follow-up, and I don't know who should get these. So
Unfortunately, we don't have the data yet from that. I suspect it was probably similar to last year, where we impacted at about 30 miles an hour.
And my follow-up is basically, Steve earlier called this a success, and I'm wondering if you could explain, because general public probably doesn't get why it would be a success when your parachute really didn't perform as hoped for or as expected.
Right. So the successful part is that we successfully conducted a supersonic experiment. So like any science experiment, it is successful if you were able to conduct the experiment, get the data you were looking for, and then be able to make conclusions from that data. In the sense it was not again and get a parachute that is able to survive through the entire event. We very much want to have these failures occur here in our testing on Earth rather than at Mars. And so it is success in that we are able to understand and learn more about the parachute so that we can get confidence and have highly reliable parachutes for when we have a large mission going to Mars where we can't do anything about it.
Okay, is there any more questions? I'm sorry, go ahead.
Thank you. Our next question will come from Alan Boyle. Your line is open, sir.
Thank you. I had a couple of linked questions. One is, it sounds as if you did get farther than you did last year with the as workable perhaps as they thought it might be to use a parachute to land large payloads on Mars. Can you provide any insight into that thinking, whether there is some discussion of whether parachutes are the right approach for the very large payloads that might be sent to Mars?
With regards to the first question, I can talk about that. Looking at the load data and some of the telemetered video data we have, the indications are that the parachute got at or near full inflation. In fact, the stills that I believe are on the website, if you look at the image on the left, it shows the parachute just cannot survive the supersonic environment any further. Parachutes are tremendously efficient decelerators. The parachute that we tested yesterday saw nearly 80,000 pounds of drag, generated nearly 80,000 pounds of drag, and itself weighs only about 200 pounds. That amount of deceleration for that small amount of mass you cannot find with any other technology presently out there. They've been critical for our missions to Mars since the Viking landers in the 1970s, and I believe they will continue to be critical as efficient aerodynamic decelerators for the coming missions to Mars.
Detectors to land, heavier and heavier masses on the planet at higher elevations. For 5 metric ton class mass payload to the surface, this technology can very well enable that. And then it's going to take to land a 20 metric tons plus for human class missions. It's going to take a combination of technologies, maybe hypersonic inflatable decelerators, deployable decelerators, mid-LOD shapes to decelerate at hypersonic speeds. Parachutes are definitely an option, as well as balloons, supersonic retropropulsion, and then propulsive deceleration. So, we have technology can absolutely do, as well as the very large mass systems that we need to enable human class missions.
Thank you. Our next question will come from Mark Carreau. Your line is open, sir.
Thank you, Mark Carreau from Aviation Week. And I have two questions, and I'm sorry I'm parsing this a little bit, but I want to make sure, first of all, with the parachute this year versus last year, this year you got inflation of the chute. Last year with the previous design, the disc design, you didn't get even that far. So that, if I understand right, Kauai next year for a similar test.
So with regards to the first question, I think last year what we saw, once we had access to the high resolution and high-speed imagery data, we saw the parachute be damaged very, very early in the inflation process. This year, with the low-resolution data that we have presently, it looks like the parachute remained largely intact, if not entirely intact, up to the point of full inflation. And we also saw more drag being generated out of this parachute this year than we did last year. So those are both pluses. But Ultimately, it's going to be the data set that we're
next experiment. We have to get a very good understanding of what happened. Fortunately, we have a tremendous amount of data that was collected on this vehicle, and as I said, that data, and Ian mentioned that data is now coming into port. And so we're going to be looking at that data in depth. If we got all that data, then I believe we'll have the information we need to get an understanding of what happened. We'll be able to remedy and strengthen and change the design of the parachute appropriately to address that, and we'll be able to conduct an experiment to get further downstream in the deployment and operation of the parachute.
Thank you. Once again, if you would like to ask a question, that will be star, then 1. To withdraw your question from the queue, that is star 2. Our next question will come.
Parachute performance on the first 2 flights, would you anticipate that one more flight, which is your current program, is that enough? If the next one is successful, is that enough, or would you anticipate needing an additional test and have a quick follow?
We have set as one of our guidelines that we need to see 2 good parachute flights in order to have this sufficient confidence in this technology to be able to infuse it in a flight project for use at Mars. And so we would want to see 2 more successful flights after this one in order to be able to say it's fully qualified. Now, having said that, there's a lot of work that we have to do to understand what happened on this flight, what we need to qualify the parachutes, how similar the tests have to be, and so on. But I think the first...
Avery Soto, your line is open.
Great, thank you so much. Thank you guys for holding this conference. I really appreciate it. I'm from the Garden Island newspaper. I was wondering, how long will it take for you and the other scientists to gather the information from the launch and analyze it?
It'll take up to about a week just to have all the data in hand. There's data that was not only on board the test vehicle, but also data that was acquired at the test range here, the Navy Specific Missile Range facility, and data elsewhere that we'll need to accumulate, safe, begin analyzing. Having gone through this process last year, but ultimately it can be months until we have a more complete picture of all the different things that took place, all the subtle elements and the contributions that they had to the overall performance of the test vehicle and of the technologies.
Thank you. Our next question will come from Miriam Kramer. Your line is open.
Hi, Miriam Kramer with Mashable. Thanks for holding this press conference. I'm just wondering what makes these kinds of supersonic chutes so difficult to build and test? This is more of a general question, and it's for whoever wants to answer it, but if you wouldn't mind just saying who you are so that I can mark that down in my notes.
For starters, they're typically deployed behind these very large blunt bodies that are going several times the speed of sound. As they're screaming through the atmosphere, they're essentially punching a hole through the sky, which air is trying to rush in as fast as it can to fill this vacuum behind the blunt body. So you have this extremely turbulent, extremely dynamic, extremely chaotic, and fast-moving wake behind this blunt body. Now you're trying to take a relatively lightweight structure, something made from nylon and Kevlar, have it inflate inside this extremely dynamic environment, and have it survive that inflation under loads that are several orders of magnitude higher. We've successfully done it several times at Mars, but as we've tried to push the envelopes of this technology, both in the scale and the conditions at which we use it, we see that there's a lot more that we have to learn about it.
I would add to that, this is Mark, we do not have an ability to simulate the operation of these parachutes in any detail. The parachute deployment and operation in a supersonic flow is extremely complicated. The flow affects the parachute affects the flow. The shape of the parachute changes through all this, and the reaction of the fabric to the flow is very complicated. And so we are not able to do tests like we just did yesterday, to see the parachute actually in flight and have the physics teach us the lessons instead of trying to get them out of the computer, which we cannot do.
Thank you. Once again, if you would like to ask a question, that is star, then 1 to ask a question. Star 1 to ask a question. Our next question will come from Zachary Wasser. Sir, your line is open.
Hi, thanks. So my editor actually, this launch kind of reminded her of the recent trailer that came out for the Ridley Scott movie, The Martian. I guess, what did this launch tell us about kind of how far on the trip to Mars when we send humans? Do we know how long that would take about?
Okay, so this is Steve Jerzik. So yeah, in addition to technology like the supersonic decelerator technology to land heavier systems on the surface of Mars, We also need to develop a suite of other technologies in order to for human missions to Mars to be safe and affordable. That includes in-space propulsion technologies to shorten trip times. It includes what we call in situ resource utilization technologies to kind of live off the land, extract fuel, hydrogen, and oxygen. It's going to take improved environment control and life support systems. So there's a long kind of suite of capabilities and technologies that we need to develop, and we have plans in place to develop those technologies, and our ultimate goal is to have humans on Mars, surface of Mars, in the 2030s.
And just to quickly answer the question on the trip time, our spacecraft to Mars today typically takes 7 to 11 months to get to Mars. That is on what's called a minimum energy trajectory. As Steve mentioned, we're looking at more advanced propulsion to try and shorten that.
Our next question will come from Irene Klatz. Your line is open.
Hi, thanks very much, and sorry for the background noise, and also apologize if this question's been answered. I'm late to the call. The $230 million that you had said before flight is what's been spent or budgeted for the LDSD program so far. Does that cover a third flight, presumably next year, and how much more would be needed for the fourth flight that may be necessary? Thanks.
So yes, that covers the third flight. It does not cover a fourth flight. We'll need to do some estimates for what a fourth flight would be at headquarters' request.
I'm showing no questions at this time. I'd like to turn the call back to Kim Newton.